Hello everyone, welcome to Skill Dev. Trey here, and in this lesson, we are going to learn about hash tables. Hash tables are a very common data structure in coding interviews. In fact, along with arrays, these two data structures are by far the most common. When you begin the job hunt and start answering these technical questions, you'll see that you use a hash table in nearly every one. So it's essential to fully understand hash tables and how to use them in interviews and really go in confident because you will use them very often. And the reason we like hash tables so much is because we can store data using key value pairs and access these keys in constant time. The good news is that there's a hash table implementation in nearly every language. This means they're used often and are easy to work with. In JavaScript, we can use objects as hash tables. In Python, we have dictionaries. And in Java, we have the map and hash table data structures. So there's a few different names for hash tables. You might have heard of a hash map, a dictionary, an associative array, or just a map. But all these names just refer to that same concept of where we use key value storage. So nearly every language has some sort of hash table implementation, and we use it to create these logical key value pair mappings. And the most common data type used for keys are strings, and we use strings because they allow us to create these logical naming for the data stored in the hash table. So we initialize the hash table variable name to the context of the problem. Here we're going to call it outside on the left. And then for the keys, we're storing things that appear outside. So outside we find lemons, clouds, sun, sky, and grass. So we have this logical mapping from the variable name to the keys for the items stored in the variable or the hash table, and then the mapping from the keys to the values. And for the values, we can store any data type we want. Here on the left, we have strings, and then on the right, we use integers. So we declare the outside hash table, we have keys of things we find outside, and then for the value, we store the color of that thing. Or here on the right, we declare a shopping cart. So we're storing the items of a shopping cart in a hash table. The keys are the names of the items in the cart, and the value is the quantity that we have stored in the cart. So we can see this kind of mapping and naming is very intuitive. We have a shopping cart with items and their quantity. And if we want to set an item or get an item, we would just call shopping cart dot that item's name. So here we said shopping cart dot tofu equals 4, and if we ever wanted to access that item, we could just access the shopping cart at the key name tofu and it would return this value. Imagine instead if we were using an array. These would be indexes instead of key names. So to access the item here, where it's currently tofu, in arrays, we would access it by index. So here we would find the shopping cart for the item at the third index. But what does this mean? Without the key name, this doesn't give us much information. What is the item at the third index? What does shopping cart of the 3 even mean? If we access the item at the third index, it would simply return the number 4 without any other meaningful information. This is why we love hash tables. With keys, we can get this descriptive naming and also access items in constant time. Hash tables and arrays are two of the most important data structures, both for interviews and on the job. However, on the last slide, you may have noticed they also have a lot of similarities. With arrays, we use integer indexes and we can access items in constant time. With hash tables, we use string keys and can still access items in constant time. So one of the primary differences is that arrays have integer indexes and hash tables use string keys. And computers understand arrays very well. These numbers as indexes are very easy to work with. It knows the first index is always 0, and then just increments those until it reaches the last item. And then memory in a computer is also just slotted by using a number, so a computer can directly and easily map between these indexes and the memory slot that the item is stored in. However, computers don't handle hash tables as easily. These string keys are harder to map to memory. So there are an infinite number of keys that we could come up with, and from the computer's perspective, they're totally random and it has no idea what to expect. So we can't easily and directly map these key value pairs to memory like we do with the sequential ordered indexes for arrays. So this makes hash tables more complex underneath the hood because we need to get them in a form that allows them to be stored in memory. And what we actually do is map a hash table to an array. So the computer underneath the hood transforms a string key to an integer. So hash tables themselves are just arrays that have been transformed. And because we get constant time access at array indexes, this is exactly what we want. So what the programming language does is send a key to something called a hash function, and all the hash function does is transform this string key to an integer, which corresponds to an index in an array stored in memory. So here, we transform the string key class into the index 7, and then it accesses this array underneath the hood, it maps this index, and stores the item in memory. So one of the main benefits with hash tables is that their big O complexity, all the operations happen in constant time. We get constant time access because all we're doing is accessing items by their key. This key is hashed into an integer, and this integer corresponds to an index in an array. And arrays can get an item or set an item at an index in constant time. So because all these operations happen in constant time, this is why we very commonly introduce hash tables to optimize solutions. So now let's discuss the pros and cons for hash tables. The first pro is one we've already discussed, and it's that hash tables are very fast. We get those constant time O of 1 operations. We also know hash tables use flexible and meaningful keys. These keys allow us to create logical and descriptive naming for data in the program, and this mapping creates readable and intuitive code. And finally, hash tables and key value pair mapping is universal. There are implementations in every language, and it's the foundation of JSON, which is one of the primary ways that we transfer data. Also for caching, we use this same key value pair mapping. So the concept of key value pairs is universally understood and can broadly be used. One of the primary cons of hash tables, and a big trade-off, is that we lose ordering. So instead of being sorted by something like an index, we give up this so we can use these named keys, which are randomly allocated in memory. Another con is that hash tables are one-way mappings. We can map a key to a value, but we can't reverse that and find a key based on a value. If we do know a value and want to find the key, we must search the entire hash table until we locate it. And finally, even though we get this fast key value access at the keys, if we wanted to iterate a hash table, it would require O of n time because we would have to grab all the keys in linear time and then iterate through those to access each item. So we said a hash function's purpose is to convert strings and other data types into numbers. They're the foundation for hash tables, but we actually see them all over computer science and software. For example, on GitHub, you may have recognized something called a commit hash. And what this is Git takes your code and all the details about the commit and then creates a hash out of them. So everything about the commit is run through a hash function, and it spits out this integer, which is used to uniquely identify a commit. And notice this integer is in hexadecimal form, so that's why you're seeing letters and numbers. Another common operation is to hash passwords. We send the password string to a hash function. Then this hash function outputs a hash integer. And once again, it's in hexadecimal form. And the reason we use hash functions with passwords is so we're not storing the password in a database. We only store the hash, which means if the database was ever compromised, the hacker wouldn't know your password. So every time you type in your password, we transform it to the hash version or the integer, and then compare that with what's in the database. And hashing is a one-way operation. So you couldn't take this hash and determine the password from it. You can only go from the password to the hash. So we're calling a hash function any function that converts any data type to an integer. That's all it does. However, there can be many ways to implement a hash function. So we need to know the requirements and what we can expect from a hash function to know that it qualifies for a good hash function. When we're using hash tables, we need to know the hash function is an effective implementation so that the hash table functions correctly. The first constraint is that hash functions should only be one way. This means we can take an input and convert it to a hash, but we can't take that hash and convert it back to the original input. So there's no way to know what the original input was from that hash. And we saw this was ideal for passwords because we could determine if the passwords match by comparing their hashes instead of using the raw passwords. You can't determine what the password was from the hash. The next constraint is that there's a fixed size output. If we're converting these items to numbers, the numbers it can take on are a fixed range. So for example, SHA-256 goes from 0 to 2 raised to the 256, and then we can hash to any value inside that range. This is also ideal for hash tables because we use an array underneath the hood, and we want the key to hash to an index that ranges between 0 and the length of the array. But one thing to note with the fixed size output, there's a limited number of values that these hashes can take on. This means it's possible that some keys can hash to the same index. When two items can hash to the same value, this is a concept known as a hash collision, and we'll cover how this works in a few slides. And having this fixed size output, this is one reason hash functions are one way. If two values can take the same hash, this means we can't figure out the value that produced this hash. The third constraint is that a hash function must always produce the same output for a given input. So with a hash table, the same key must always hash to the same index. If the hash function wasn't consistent, then this means the key could go to a different index, and then we wouldn't be able to correctly get and set a value. The fourth constraint is that all output values are equally likely. This ensures that when we call a hash function on different values, they will distribute evenly across the range of values. This ensures in a hash table that we won't get too many going to the same index. And finally, a hash function should work with any input type or any scenario. So we most often use it with strings for hash tables, but it should work with any data type, because at the end of the day, all data types are ones and zeros underneath the hood. So you should be able to pass any data type to a hash function. And one example of this, when you download files, you might notice a download hash. And what this does is allow you to compare what you downloaded to what the provider is telling you that you should have received. So you hash the downloaded file and compare that hashed output to what the server says. This allows you to make sure you didn't download the incorrect thing and potentially get a virus or some other malware. So if the hash function follows all of these 5 constraints, we know it's a good hash function and we can effectively use it with the hash table. So the single and sole purpose of a hash function is to convert strings and any other type of data into an integer. And the name hash function just refers to a broad category of functions, all of which their sole purpose is just to do this, to create integers out of other types of data. But there are many implementations and algorithms that can achieve this. Some you may have heard of are MD5, SHA-1, and SHA-256. They all have the same goal, but the difference is how they're implemented and their algorithms, and then the total number of integers that they can take on. For example, MD5 can have 2 raised to the 128 integers. SHA-1 can be any integer 0 to 2 raised to the 160. And SHA-256 is the largest of the three and can be an integer between 0 and 2 raised to the 256. And on the skilled.dev website, I actually created a SHA-256 generator. So if we type the word skilled in, the SHA-256 hash output is this number here, and this number is represented in hexadecimal form. And if you type the word skilled with a capital S, every SHA-256 generator or implementation is always going to produce this number. Hashing algorithms must be consistent and must produce the same output for the same input. They also must be distributed evenly. So notice if we convert the capital S to a lowercase s, it gives us a totally different number. So even though it seemed like a small change to us, in order to fulfill the constraint to be broadly distributed, it created an entirely different number. So this is something I encourage you to play around with and really see how hashing can change from the input to the output. And notice that it's nearly impossible that you'll ever get the same output because the total number of integers for SHA-256 is 2 raised to the 256, which is a very, very large range. Memory in computers is a limited resource. There's simply a maximum amount of data that any computer can hold. Because it's a limited resource, we have to learn how to be efficient with it and know how to manage it effectively. This is one reason we care about that big O space when we're judging the quality of algorithms. And as we've discussed, when we create a hash table, underneath the hood, the programming language creates an array in memory. So this means the array must be a fixed size. And then when we store values in the hash table by a key name, it maps this key name to an index in that array. So since memory is a limited resource, we want to be smart about how we use it. So it wouldn't make sense to declare an array underneath the hood with 1 billion items initially. This would be taking up 1 billion slots in memory, and we wouldn't even be using them. So what programming languages do is when it creates this array underneath the hood, it creates it at a fixed smaller size. Then as we continue to add items to the hash table, it grows this array size underneath the hood to account for all those additional items. So memory is a finite resource, and the array is a fixed size. However, the key names we can come up with are unlimited. There's an unlimited amount of combinations of characters we can come up with for these keys. So we have the finite resource in memory, and we want to map these unlimited possibilities of key names to this finite resource. Since the key names we're coming up with are random, or at least random from the computer's perspective, and there's an unlimited amount we could come up with that we're trying to hash to a limited range of integers, it's possible, and even likely, that some of these keys will map to the same index. This is what's known as a hash collision. So a hash collision occurs when two different input values map to the same integer index. On this slide, we have a very simple and naive hash function where we're taking a character's UTF-8 encoding and then summing all these encoding values together to get the integer as the hash output. And we see the string inputs are different, skilled, and covered. However, the output for them is the same integer. So in this case, we have a hash collision. So we need a way to handle hash collisions. If we went to store two values that hash to the same index, we wouldn't want the second one to override the first one. We want a way to store both values at this index. And then also, when we go to access one of these items by its key, we want to make sure we find the right item at that index. And the way we do this is at each index, instead of storing the items, we create a linked list and we store the key and the value for that item. So we call these buckets. And here we have John Smith and Sandra D that both hash to 152. So we create a linked list, and this linked list stores the key and the value. And then when we go to look up an item, we hash it to the index and then iterate through the linked list until we find the matching key. And here's just another image to help you visualize what's happening. We have the hash table on the left. We hash the keys to an index. And then at that index, we have buckets for a linked list, where we store the key and value of the item. So one thing you may have noticed is that we're iterating through a linked list, and we usually assume this takes O of n time. So how can we assume hash tables operate in constant time? And to do this, we assume there has to be a good hash function, and the size of the array is sufficiently large. If these aren't true, then the hash table does operate in O of n time, but if they are true, then we get those constant time operations. And you can assume this will always be true. Hash table implementations for all languages are implemented well and will pass these constraints to get constant time operations. So the first constraint is that we need a good hash function. We need it to assign this key to a bucket or an index uniformly so it's evenly distributed. We also need to assume that the hash function itself is just efficient at calculating the hash. And if it's not efficient, or they're not evenly distributed, we see that it could overweight a bucket, and then send too many items to it, then it would require this O of n time to iterate the linked list stored in this bucket. We also need to assume the size of the array is sufficiently large. If we don't have enough items in the array, then we're going to send too many items to each bucket and then once again get these O of n linear time searches. So let's look at the most prominent ways hash tables are used in interviews. The first is that a hash table is often not the input to the question. We're actually given a different data structure, and then we use a hash table to get the fast operations and optimize a solution. To get these fast constant time operations, we make the trade-off to add O of n space to create the hash table to get the fast operations. And finally, the input data structure is often one that is ordered, and then you introduce the hash table to get the constant time operations, and then get these lookups when you iterate through this ordered data structure. And those are hash tables. Thanks everyone, and I'll see you in the next lesson.